Welcome to Structural Dynamics class. In this class, we will study numerical methods. Let's go to the outline of the class. So, methods of solving differential equations. So, we will discuss about that, and arbitrarily varying force, time stepping methods, and what are the requirements for numerical methods, and methods of numerical analysis. So, these things we are going to discuss in this class. So, methods for solving differential equations. So, this is a system, a single degree of freedom system where mass of slab is present. It is supported by two columns and damping. As you can see here, mass is present here, stiffness of supporting columns and damping are present in the system, and then excitation. Okay. Then we can idealize this system as a single degree of freedom system. So, the equation of motion or governing differential equation will be of the form mu double dot plus cu dot plus ku is equal to P. So, P is a force and this mu double dot, cu dot and ku are inertia force, damping force and stiffness force respectively. Now, when P acting on the body, we know how to solve this one. So, these are the methods. So, there are four methods for solving and then find the solution. Solution what we want is u of t we want to find solution. So, first one is classical method, second one is Duhamel's integral method, we have discussed that, and the third one is transform method. So, we have discussed Fourier transform, how we convert time domain into frequency domain, that we discussed in Fourier transform method. And Duhamel's integral method, what we did was we took the random forcing function and then divided that into a series of impulses, and for one unit impulse we found the response, and then from there we found out the response to impulse and then integrated over a period. So, wherever we want we can get the response. So, that is what we did in the Duhamel's integral. And classical method of solution also we have discussed, where forcing function is sine or cos. So, now in this class we will discuss numerical methods. So, what are the applications of numerical methods? So, when do we apply numerical methods? So, numerical methods we apply when excitation, so that excitation or the applied force or ground motion varies arbitrarily. When it is varying arbitrarily, so we cannot go for classical method or other methods. Then the second one is when the system is non-linear. So, all the other three methods can be more or less can be used to find out the response of arbitrary force also, but when system becomes non-linear, then we have to rely on numerical methods. Now, arbitrarily varying forces. So, let us discuss that. So, this is a single degree of freedom system, an idealized single degree of freedom system where mass is there, stiffness is there and damping is there. So, as a structural engineering application, if we take single story building, so all the mass we assume it to be concentrated at the roof level. So, that is at the center of mass, because more mass is there at that location, and all the supporting say columns and walls put together are offering stiffness K, and the damping which reduces the energy of vibration. So, we call that as a damping factor, that is damping C, and then force P is acting on the system. So, if force is, so this one in terms of ground acceleration it is acting, so that force can be calculated as P is equal to mass times acceleration. So, that is force. If force is, this random force is acting, how do we find out? So, for elastic systems, equation of motion will be, we know this one. For elastic systems, equation of motion will be mu double dot cu dot plus ku is equal to Pt. So, in this one, the stiffness is elastic, force is random, whereas for inelastic system, force, that is stiffness force is dependent on displacement as well as velocity. Here it is dependent only on displacement. So, we can solve this one by using initial conditions, that is u0 is equal to 0 and then u dot 0 is equal to 0. By using initial conditions we can solve this one. Now, time stepping methods. So, in time stepping methods, like we discretize the forcing function, that is force, into different time intervals. So, like this we discretize that and then give I plus 1, I plus 2, that is t at I plus 1, t at I plus 2, like that. So, forcing function, and then you can see this is the response at time t is equal to t1. This entire equation will become m into acceleration at u1 double dot and damping into velocity at time t is equal to t1, that is u dot I, and displacement at that time t is equal to ti, that is ui multiplied by k, that should be equal to force at that time instant. And then if say time t is equal to ti plus 1, then this equation should hold good, that is acceleration at time ti plus 1, velocity at t time I plus 1, and displacement at time I plus 1. So, that should be equal to, all these products should be equal to force at time I plus 1, as you can see in this one. So, force at this point, okay, should correspond to the displacement at I, and force at p I plus 1 is corresponding to, or displacement at I plus 1 is corresponding to force I plus 1. So, here you can see this equation of motion for time t is equal to ti, and here the equation of motion for time t is equal to ti plus 1. Now, how do we solve this one? We have written equation, but how do we solve this one? And now, when we are solving like dynamic equilibrium equation using numerical methods, what are the conditions? So, first one, the solution should converge. So, what is the meaning of convergence? As the time step decreases, the numerical solution should approach exact solution. So, that means what? If say excitation is, for example, say for 30 seconds, if my say time step delta t is say 0.01 second. So, that means what? How many times it is? 30 divided by 0.01 second. So, that many in times I am solving this equation. As the time step is decreasing, solution should approach to the exact solution. Whatever classical solution gives, it should be near to that solution. But as time step increases, so what happens? So, we will get the approximate solution, not the accurate solution. So, convergence means as time step decreases, it should converge, solution should converge. That means what? Solution should be, so for example, if displacement function, the original displacement function is this, the final solution, so that is t and u of t, then approximate solution should be near to this one. And as the time step is decreasing, then it should match the exact solution. That is what is said in the convergence. Then the second one is stability. So, stability means what? It should be, the solution should be stable in the presence of numerical round of errors. So, this numerical round of errors will occur, but the solution should be stable enough. So, that means what? Wherever we are getting solution, that should be near to the accurate one. It should give approximate value, but it should be near to the accurate results. Then the accuracy, third one. So, the procedure should provide the results close enough to the exact solution. So, these three things are there as a criteria for numerical methods, as a requirement for numerical methods. One is convergence, second one is stability, and third one is accuracy. So, solution should converge to exact solution as the time step decreases, that is convergence, and it should be stable in the vicinity of the solution, that is the stability, and the accuracy is the procedure should produce close enough results, that is accuracy. Now, what types of numerical methods are available for solving dynamic equilibrium equation? So, first one is like stepping from time ti to ti plus 1 needs approximate methods. So, what are the approximate methods? So, there are methods which are based on interpolation of excitation function. So, as force is an excitation function, so if we start interpolating this excitation function, so that means what? We break down into small components and try to find out solution for each component and later add them. So, that is the first one. And the second one is methods based on finite differences of velocity and acceleration. So, we have this quantity displacement which we are trying to find out as a solution of the dynamic equilibrium equation. Okay. So then the derived quantities are velocity as well as acceleration. So methods based on finite difference expression for velocity and acceleration. This is the second type of methods. So in this we discuss about three methods, that is forward difference method, backward difference method and central difference method. So for our dynamic equilibrium equation solution, for finding solution to dynamic equilibrium equation, we use central difference method in this case. And the third one is methods based on assumed variation of acceleration. So in the forcing function, acceleration is there. So force is equal to mass into acceleration. This acceleration is the actual input. So now this acceleration, how it is varying. So in between two time intervals, say time ti and time ti plus 1, how the acceleration is varying. It to vary linearly, or we assume average between these 2 points. So whatever acceleration is there at ti and whatever acceleration is there at ti plus 1, we average it and take that average in between these two time interval. Or there is another way, is we linearly vary that. So that means whatever is acceleration at ti and whatever is acceleration is ti plus 1. So we will not use the forcing function, but we will take a linear variation in that. So care should be taken such that the time interval is very small, so as we are not losing the accuracy of the problem. So in this class we have discussed the necessity of the numerical methods. Okay. So what is the necessity of numerical methods? Numerical methods are needed in two conditions. Okay. Number one, when force is random in nature. Number two, when the system is non-linear. So in these two cases we will use numerical methods. And then the types of numerical methods, or the essentials of numerical method, we have discussed. One is convergence, second one is stability, and third one is accuracy. And then later we have discussed the types of numerical methods available. So first one is interpolation of excitation function. Second one is finite differences between the velocity and acceleration, and third one is assumed variation of acceleration.